Hi everybody, I hope this video finds you well. In today's video, we're going to be working through the practice number 2 that's posted on your Canvas site. This practice is related to quantitative variables, so I would recommend that if you haven't already worked through this practice on your own, you should stop this video and try these 3 questions yourself. Remember that to be comfortable working through these 3 questions, you will need to have watched the quantitative variables videos 1 through 4. If you've watched those videos and you've attempted these practice problems, then definitely proceed to go ahead and watch this solutions video. Also keep in mind that if you're just interested in the solutions themselves, in other words, if you just want to check your answers, the solutions document can also be found on Canvas and is also linked in the description below. So let's get into talking about each of these questions that deal with quantitative variables. So our first one has 4 friends, Amy, Barry, Carla, and Dave, carefully alphabetically named here, and they all go bowling. So they each bowl 8 games and record their scores for each game. And so they get the following data. So the way to sort of read this table is here's the games, game 1, game 2, game 3, game 4, etc. And here's each of the 4 friends. So you can sort of see that in game 1, Amy got an 85, whereas in game 6, Carla got a 98. In game 7, Dave got a 105. For bowling, scores can technically go anywhere from 0 if you were to miss all 10 of your frames and not hit a single pin, all the way up to 300. So we've got this data that's telling us the score that each of these 4 friends got on each of the 8 games they played. So we're going to analyze this from a bunch of different perspectives. We're going to try to figure out which of the 4 friends had the best score on average, which of them had the best median score. We're going to determine which of the 4 friends was the most consistent based on standard deviation. We're also going to say which of the 4 friends had the best single game score, and we're also going to determine which of the 4 friends won the most games, basically going game by game and comparing their scores. So let's go ahead and talk about each of these. So we'll do this, we'll do most of our computation and work on the next sort of page here. So here's the data sort of rewritten just so that we have this as a reference. Let's go ahead and start without even thinking about trying to answer the questions, just getting some of the key sort of statistical measures here. So we'll go ahead and we'll make an additional sort of couple rows here. We'll calculate X bar, S, and the median for each of these. These are the ones that are sort of referenced in those questions. We need to know about average, standard deviation, and median. And you'll notice that I'm using sample standard deviation. Even though it doesn't say whether or not this is all the possible games they've played, it just seems reasonable to view this data as a sample. So let's go ahead and type this data in. So we'll start by calculating these things for Amy. So let's put in 8, and we can hit stat, edit, and start typing in the data. 85, 78, 105, 110, 115, 98, 93, and 72. Then we can hit stat calc 1 var stats. And if we go ahead and calculate that, we can see that for Amy, her average score was 94.5. Looks like her standard deviation using the sample one was 15.4, and her median score was 95.5. Okay, let's do the same for Barry. So we'll go stat, edit, and put in our second set. You can put this, you can clear out the data for Amy since we already got the key statistics, or you could put Barry into a separate list. It's up to you. Either way, we need to put in 73, 72, 76, 135, 149, 81, 102, and 76. Stat calc 1 var stats to calculate the descriptive statistics for him. So for Barry, it looks like the average was 95.5, standard deviation 30.5, and median score looks like 78.5. All right, same thing for Carla. So stat, edit, either clear out one of the previous lists or put it into a new one. 68, 65, 73, 71, 210, 98, 71, and 55. Then stat calc 1 var stats for her data. Looks like the average there would be 88.9, and the standard deviation 50.4, and median looks like you should get 71 there. Finally for Dave, stat, edit, either put it into a separate list or clear out one of the previous ones. 86, 80, 63, 61, 50, 100, 105, and 78. then stat calc 1var stats, and we'll go ahead and calculate for him. Looks like his average score was 77.9, standard deviation 19.2, and then median looked to be 79 there. So there we go. Now we have all the sort of main measures that we like to use, and now we can actually begin by answering the questions. So if we go back and we take a look, right, part A said, which of the 4 friends had the best score on average? So if we take a look here, average for Amy was 94.5. Barry just barely beat her out there, 95.5. Carla seems to be in third, 88.9, and Dave was sort of in last in terms of average, 77.9. Notice that since we're talking about bowling scores here, we certainly are using the higher the score, the better they did, right? There are certainly things out there, say like a reaction test or the time it takes you to complete some task or some puzzle where lower scores would be better, but certainly in bowling, the higher the score, the better you did. So in terms of average, we would pick Barry as doing the best. His average was 95.5. So Barry with an average score of 95.5 points per game. So there we go. So in terms of average, Barry sort of seemed to do the best there. Now, does that mean that he is the best bowler amongst these group of 4 friends? Well, if we decide that average is the way we want to measure that, for sure, right? He is the best, just slightly above Amy. But of course, we have other ways of measuring sort of the center or the typical value, right? I mean, that's why average seems to make sense, right? I mean, if you want to sort of know who typically does better, well, average seems to be a good choice. But we also talked about using median. So for B, I believe we wanted to diagnose which of the 4 friends had the best median score. So if we look at this, in terms of median scores, it's not really close, right? Amy had a 95.5 median, and Barry, Carla, and Dave were all in the 70s in terms of median. So in this case, we'd say Amy with a median score of 95.5 points per game. So you can see that we get sort of a different answer, right? Amy instead of Barry, if we use a different measure. And this is sort of the whole point of statistics, right? In statistics, we're trying to see how using different measures can give us a different perspective on the data. Now, the reason why Amy has such a better median compared to everybody else is going to become apparent when we answer part C. So let's think about part C here. Part C says, which of the 4 friends was most consistent? Now, keep in mind, consistency is not necessarily good or bad. You could be consistently the worst bowler. You could be consistently the best bowler. Consistency just means you're consistent. You usually perform about the same every time. So how would we decide who's most consistent based on standard deviation? Well, keep in mind, standard deviation means we're measuring how spread out the data is. The higher the standard deviation, the more spread out. That means if you want to be consistent, you should have a low standard deviation. So if we look at this, who had the lowest standard deviation? Well, Amy was 15.4. Barry and Carla had much higher standard deviations. Dave was a little bit higher. So we would say Amy was the most consistent. Amy was most consistent with lowest standard deviation of 15.4 points per game. Now, does that make sense just taking a look at the data? Well, certainly you can see like Barry and Carla had scores all over the place. You can see Barry had games where he was getting in the low 70s and then games where he was getting in the mid 100s. Carla's even more extreme. She had games where she was as low as in the 60s and 50s, and she also broke 200 at some point. So they're all over the place. Amy, though, and Dave, as you can see, much more consistent. Amy's generally looks like in sort of the 80s and 90s, a few games a little lower in the 70s, a few games a little higher in the hundreds. Same thing with Dave, some 80s, 70s, a few lower games in the 50s and 60s, a few higher games in the hundreds. So you can see how the standard deviation being smaller here basically indicates a higher level of consistency. Now, We said that that would sort of explain what was going on here. Well, you can see why Amy, by having sort of the lower standard deviation being more consistent, would therefore also have a solid median score. She doesn't drift that far from that median performance. Okay, let's go ahead and look at some other ways to analyze this. So, D said, which of the 4 games had the best single game score? So forgetting about average or median, who just did the best any one time? Well, if we look at this, Amy's best score out of all 8 of these games was 115. Barry certainly did better. He had a game where he had 149. Carla was even better. She had a game where she was all the way at 210. And Dave's best game actually came in game 7, where he got an 105. This time, there's no doubt, right? Carla had best single game with 210 points. So if we were just saying who did the best in one single game, there was no doubt. Carla was far and away. The next closest score was a 149 by Barry. She beat that by more than 60 points. Now, the rest of her games, not very good. And that's why she had such a high standard deviation and a pretty low average and median. But she had that one single really strong performance. All right, let's look at one more way of analyzing this. So part E asks, which of the friends won the most games? So now we're thinking game by game, who won or had the highest score in each game? Well, if we look at this, game 1, Amy 85, Barry 73, Carla 68, Dave 86. So if we're circling sort of the winners there, Dave would win that first game. In game 2, 78, 72, 65, 80, again just barely, Dave won game 2. Game 3, looks like Amy won with 105. Nobody else was very close. In game 4, it looks like Barry won. Again, nobody was very close there. In game 5, Carla had her dominant performance. Definitely she won there. Game 6, just barely, Dave beat out Amy and Carla, so within 100. Then in game 7, looks like Dave also won with a 105, with Barry in second at 102. And then in game 8, well, looks like Dave won again, 78, versus a second place by Barry of 76. So notice, by changing how we assess what's good, we get a different answer this time. If we're going game by game, out of the 8 games that these people played, Amy won once, Barry won once, Carla won once, and Dave won 5 times. So Dave won 5 out of 8 games. Everyone else only won once. So my whole point with this sort of example here is to recognize that changing the measure you use, how you measure, in this case, success at bowling, changes who might be the best. If we're talking about average, Barry was barely the best, right? He just managed to be higher than Amy in terms of average. In median, it wasn't even close. Amy was by far the best. In terms of single game performance, Carla should be the happiest. 210, nobody was even close. In terms of if these friends were competing each game, well, Dave won 5 out of the 8 games. Everybody else only won 1. So, as you can imagine, this should show you how challenging it can sometimes be to make a decision in statistics, because depending on the measure you're using, you can get very different conclusions. On the flip side, though, it also tells us that we can get a ton of different information based on just very simple data, like the scores that people have in a game. You can sort of analyze that from a lot of different unique perspectives. All right, so this was question 1. Let's go ahead and take a look at question 2. So for question 2, we're back to more of a standard sort of statistical sample. In this one, we were studying the lengths of western diamondback rattlesnakes. To do this, it says you randomly capture 19 rattlesnakes and you measure their lengths in inches. So you get the following data. So there was a rattlesnake that was 37 inches, one that was like 52 inches long, one that was all the way up to 72 inches long. We're going to identify the population, sample, and individual, the sampling technique. We're going to calculate the mean, median, and standard deviation. We're going to construct a histogram, build a stem plot, use both of those to describe the shape, and then also decide what percentage of our sample measured longer than 55 inches. So let's go ahead and start with the standard population, sample, and individual. Well, our sample should be clear. We measured and captured 19 of these rattlesnakes. So I guess we would say 19 Western diamondback rattlesnakes. That means an individual was one Western diamondback rattlesnake, and the population would be all Western diamondback rattlesnakes. So there we go. There's our population, sample, and individual. For part B, what technique was used here? Well, the key word for that is it does say randomly. So we know that that means it was either an SRS, a stratified, or a cluster. We didn't choose these rattlesnakes from different areas, which might make it stratified. We didn't find groups of rattlesnake and randomly select entire groups, which would make it cluster. We know we just did this randomly. So the technique here would be an SRS. All right, let's go ahead and calculate the mean and median and standard deviation. So some basic measures here. So to do that, we'll need to put this stuff into our calculator. So if we hit stat and edit, and we can clear out the data from the previous problem, then we can start putting this in: 37, 40, 43, 46, 46, 49, 50, 52, 52, 52, 54, 56, 58, 58, 59, 62, 64, 69, and 72. So we do have 19 data points there. Then stat, calc, 1 var stats. And if we run that, we want to record the mean, which looks to be about 53.6. And of course, the units would be inches. The standard deviation, of course, we would use it as a sample because it is a sample here, would be 9.3 inches. And the median looks like it should be 52 inches. So there we go. There's some of our basic statistical measures: mean, standard deviation, and median. All right, let's go ahead and maybe I think we'll continue this on to the next sort of page here. Let's grab our data. Okay, and we'll copy them. So let's give ourselves a blank page. We'll just put that up there. Okay, so the next thing we wanted to do is we wanted to create a histogram, class size 10, starting at 30. So let's go ahead and do that. So this would be part D here. So we said class size 10, starting at 30. So we need to make our classes and get our frequency. So we were told to start at 30. So our first interval would be 30 to, and then since the class size is 10, we'd add 10, so 30 to 40. Remember, we will include the left endpoint and exclude the right endpoint, so hard bracket and soft bracket. Next class will start where this one left off, so 40 to 50, then 50 to 60, then 60 to 70. Notice we do have a 72 though, so we do need to go one more, 70 to 80. Now we can count the frequencies. For 30 to 40, it looks like we just have 1. For 40 to 50, we would have 1, 2, 3, 4, 5. So there we go. And we can use some lines to help us sort of visualize that. Remember, 50 would go in here because we include the left end and exclude the right end. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. So we have a frequency of 9 there. 60 to 70 looks like 1, 2, 3. So we have a frequency of 3 there. And then we have that 72, so a frequency of 1. We can check and sum these up. 1 plus 5 is 6. Plus 9 is 15, plus 3 is 18, plus 1 is 19. So, of course, it matches the sample size. All right, now we can go ahead and draw our histogram. So remember, our frequency needs to be here. So we could go like 2, 4, 6, 8, 10. So as long as we have a consistent scale that starts at 0. And then here we can label our axes: 30, 40, 50, 60, 70, and 80. And of course, we want to label this as the length in inches. So we can go ahead and draw our bars. First one is a height of 1, so there we go. Then a height of 5, so there we go. Then a height of 9, there we go. Height of 3, and then a height of 1. Okay. If you're ever a little unsure if your graph is easy to read, you can also always include the frequencies inside, so 1, 5, 9, 3, and 1 to make it a little bit easier. What sort of shape would we describe this? Well, we can sort of see it goes up like that and then comes down like that. So we would probably call this approximately bell/normal. Okay, so there we go. We've built a histogram with class size 10 starting at 30, and we've diagnosed that the shape or the distribution should be bell or normal. Bell normal, remember, is an example of a symmetric distribution, which means that the mean and median should be roughly the same. If we go back and check where we calculated that, notice our mean was 53.6, our median was 52. Those are very close to each other, so it makes sense that we got a symmetric distribution here. All right, we've got a couple more things to do. We'd also like to create a split stem plot and describe the shape. Now, of course, just because we switch displays doesn't mean we should change the shape. So we're still expecting a bell or normal distribution, but we just like another visualization. So we're going to do a stem plot. So let's go ahead and take a look at the stem plot here. So if we look at our data set, looks like we'd have stems of 3, 4, 5, 6, and 7. But we are doing a split stem plot, so this is a split stem plot. So remember, we're going to write each of those twice. So 3, 3, 4, 4, 5, 5, 6, 6, and 7, 7. All right. Any leaves 0 through 4 for a stem of 3? Well, no. Only leaf is going to be 7, so it's going to go in the second one. Then the 40 and 43 will go in the first 4 because they're leaves 0 through 4. And then the leaves of 6, 6, and 9 will go into the next one. So 6, 6, and 9. For the first 5, we'd have the 0, 2, 2, 2, and 4. So that was 0, 2, 2, 2, and 4. Then for the second 5, any stems with a leaf of 5 through 9, so that would be the 6, 8, 8, and 9. So we said 6, 8, 8, and 9. Then for the first stem of 6, we'd have the 62 and the 64. So 62, 64. Then we'd have that 69 for the second stem. So 69 there. And then the final 72 would go here, because it's a leaf of 2, so it would go in the first 7. Now, notice it's a different visual display than we saw here. It's a little bit more precision because here the class size was 10, and since here we are splitting it, it's basically actually like a class size of 5. But as you can see, the shape is the same. We sort of got tails to both directions, or if you were to actually sort of draw this thing out, you could imagine it sort of looking like this. And as you would expect, it is still approximately bell normal. Now, since this is a stem plot, we should write out our key here. So I always just like to use the first one. 3/7 does mean 37 inches in this case. All right. So main thing to see here is 2 different visual displays. Keep in mind, though, that just because you change the visual display certainly does not mean you should change the shape. The shape is sort of intrinsic to your data. The visual display is just a way of sort of seeing it. So just because we switch from a histogram to a stem and leaf plot, the shape should remain the same in both. All right, lastly, we had a percentage I think we wanted to calculate. We wanted the percentage of the sample that measured longer than 55 inches. So since it's the percentage of the sample, we know it's going to be out of our sample, which was 19. So let's go ahead and do that. It's going to be something over 19. We want them to be longer than 55 inches, so we can just count. Looks like it would be 1, 2, 3, 4, 5, 6, 7, 8. So there were 8 of these rattlesnakes that were longer than 55 inches. So it would be 8 out of 19. We can divide that on our calculator, 8 divided by 19, and that should give us about 42.1%. So, in other words, our answer would say that about 42.1% of our sample were rattlesnakes that measured longer than 55 inches. In other words, 8 out of the 19 we looked at had this property. Alrighty, so this was question 2, which was basically running us through some of the review stuff about population, sample, individual, some of the basic measures for quantitative information, and 2 of the visual displays, as well as a brief discussion about shape. Alright, let's move on to question 3, which takes a look at the other visual display, as well as our discussion of outliers. So, for question 3, it said that you're interested in studying how many books El Camino students read for fun. So to do this, you set up a table on the campus from 12 p.m. to 3 p.m. with a sign that says, "Come talk about reading." Any of the students that walk over, you ask, "How many books have you read in the past year?" 14 students come by and talk to you, and you get the following data. So a couple people said 0 books, some people said 2, somebody said all the way up to 33. We're going to start by sort of the basic definition part, population, sample, individual, and sampling technique. We're going to give the 5-number summary. We're going to draw a box plot. Remember, the box plot is a visualization of the 5-number summary. And then we're going to check for any outliers in this data set. What looks like it might potentially be an outlier? Well, maybe this 33. It seems much larger than the other data. If anything's an outlier, it's most likely that 33. Let's go ahead and start this, though, at part A. So, population, sample, and individual. Well, we can see that we ultimately talk to 14 students, so we know our sample is 14 students from El Camino, or from ECC. The individual would be 1 student from ECC, and of course the population would be all students from ECC. We've done a lot of these at this point, but this is also just a good chance to remind yourself the variable should not show up here. Notice there's no mention of the number of books that these people have read for fun. That's the variable. It doesn't have any place in the population, sample, or individual. Because again, maybe we ask these people many questions, right? They would still be the same people, but the variable would change. So that variable, the number of books read, should not appear in your description of the population, sample, or individual. All right, let's go ahead and identify the sampling technique. So the technique here, I think to save a little space, let's put that over here. The technique. Well, if we read through this, there was definitely no randomness. You set up a table. You just have students that walk over, you ask them the question. Now, walking over and setting up a table, that's not a system, right? You're not choosing every 50th student or every 10th student that exits a particular building. You're just letting people come up to you. So the technique here would be a convenience sample, which actually means in terms of like inferential statistics, trying to make a decision based off of this data is considered invalid. We can still do all of our descriptive statistics, we can still visualize the data, but we certainly wouldn't feel comfortable extending this data to the rest of the population because it wasn't gathered in a random, statistically valid fashion. But this would be an example of a convenience sample. All right, let's go ahead and get that 5-number summary. So 5-number summary. Remember those 5 numbers are the minimum, Q1, the median, Q3, and the maximum. So if you want, you can type this data into your calculator and do it that way, or we can just look at the data. Either way, though, I'll just go ahead and pop the data in. So stat, edit, we'll clear out what we just got from the previous problem and type in this stuff, 0, 0, 2, 3, 4, 4, 5, 7, 9, 13, 17, 18, 22, and 33. And we do have 14 data points there. Then stat calc 1 var stat. We can ignore the average and standard deviation. I mean, we could write them down if we wanted to, but they're not part of the 5-number summary. So the minimum is 0, Q1 is 3, median was 6, Q3 was 17, and the maximum was 33. All of these, of course, would be in books. So the minimum number of books read was 0, maximum was 33, everybody else was sort of in between. Let's just go ahead and just to confirm that we understand what all that stuff means, that it really does work the way it's supposed to. So if we look up here, if we were doing this manually, we have 1, 2, 3, 4, 5, 6, 7 data points. So our median would be right there, where there'd be 7 on this side, 7 on this side. It would be between 5 and 7. What number is directly between 5 and 7? It would be 6, and that's exactly what we got here. Then, if we were trying to divide up this part, we'd have 1, 2, 3, and 1, 2, 3. So Q1 would be right there. So Q1 should be 3. Oh, yep, absolutely. And then over here, 1, 2, 3, 1, 2, 3. Yep, if we put our Q3 right there. So notice we have 3 data points, 3 data points, 3 data points, and 3 data points, 4 equal pieces based on these 3 quartile values. Okay, now again, the calculator is always going to give the right value, but just because we introduced this stuff just recently, it's a good idea to just go back, confirm you really understand what those quartiles, and especially what the median is doing in terms of splitting the data directly in half. 50% below the median, 50% above the median. All right, we'd like our box plot here. So remember, first thing to do in a box plot, we are going to draw ourselves a nice axis. We want to go from 0 to 33, so we can maybe go 0, 5, 10, 15, 20, 25, 30, and 35. That'll be sufficient. And of course, this is number of books read for fun. Okay, we start our box at the first quartile, which is 3, so that looks like we'd start it somewhere right about there. The median, or the Q3, is at 17, so that would be right about there. There's the actual box. Then, of course, we put the median, a line at the median, that's at 6, so we would be right there. And then we put out our sort of whiskers, or the lines to the minimum, which would be 0. And out to the maximum, which would be 33. All right, there we go. What shape are we seeing? Well, don't worry about that. Don't worry about that. Just focus on this. Keep in mind this distance is very short, much longer section out to the right. So the shape here would be approximately right skewed. That's what the box plot is telling us. If you still have your data in your calculator, you can do a quick check of this by going back and taking a look at the mean for this data. The mean, if you have your calculator in front of you, was 9.8. The median was only 6, so you can see that the mean is about 50%, over 50% larger than the median, so that confirms that right skewed sort of shape there. All right, we had one last sort of thing we wanted to do, was we wanted to talk about, are there any outliers in the data set? So in other words, we want to know, does that 33 really sort of count as being extreme compared to what the other people said? So let's go ahead and do that outlier check. So first thing we want is the IQR. Remember, the IQR is Q3 minus Q1. In this case, that's 17 minus 3, which is 14. Then step 1 of the outlier check, we need to get the lower bound, which is Q1 minus 1.5 times the IQR, which in our case is 3. That's the first quartile, minus 1.5 times 14. You can type that directly into your calculator, and if you do that, 3 minus 1.5 times 14 should get negative 18. So if anybody read less than negative 18 books, it would be an outlier. Obviously, that's impossible, so there aren't going to be any outliers on the low end. The upper bound, we start with the other quartile, Q3. We add 1.5 times the IQR, so this time we go up from the third quartile. So 17 plus 1.5 times 14. If we type that in, 17 plus 1.5 times 14, we would get 38. So if anybody had said that they read over 38 books, we would consider that an outlier. Notice that all of our data, right, all of our data from 0 up to 33 lands inside that range. 0 is in that range, 33 is in that range. So this time we would say no outliers. All data is between lower bound and upper bound. So while the person who said they read 33 books seemed like a lot compared to everybody else, it's not so far above the rest of the data to be considered an extreme outlier, right? Somebody would have to read more than 38 books, according to our data, to be considered a true outlier in this situation. So there we go. There's 3 sort of practice problems related to quantitative variables.